Alright, so in this video, we're going to be covering the exponential form of complex numbers. And for this, we're going to be using Euler's formula, which says that e to the theta I, or I theta, is going to be equal to cosine theta plus I sine theta. So essentially, it's just going to be equal to cis theta, right? And this also means that if you have a number in front of r, like 2 or something, that's also going to be in front of, r cis theta. So we can generalize this to r e to the theta I is equal to r cis theta. Okay. And so let's see how this is useful. Okay. So let's say we have the number negative 1/2 plus square root 3 over 2i. Now, as we can probably figure out by looking at this, this number is going to be at a cosine of, well, it's negative. If we have negative 1/2 plus square root 3 over 2, right, that's going to be at the coordinate negative 1 over 2. So cosine theta is going to be negative 1 over 2, and then sine theta is going to be 3/2. So it's going to be somewhere over here, and our angle, we know, is going to be 2 pi over 3. So we can say that this is equal to 1, because the radius of this is 1. It's right on the unit circle. And then this is equal to just cis 2 pi over 3. Okay? So this in exponential form can be represented as, so r is 1 because our radius is 1. It can be represented as e times 2 pi over 3i. So you might be like, oh, okay, I get it. It can be represented that way. Why is this useful? Well, like that it's not. But this becomes really useful when we're dealing with stuff like finding roots of unity or multiplying complex numbers. So let me show you what I mean by that. Let's say we have the complex number 2 square root 2 minus 2 square root 2i. And yes, we could divide this. We could pull out a 4 and be like, oh, this is square root 2 over 2 minus square root of 2 over 2i, and find the angles like that. But let's actually do this a different way. All right, so we want to put this into the form r cis theta, right? And so how are we going to do this? Well, let's do it the way where we need to find r using our knowledge of magnitudes. So what this looks like on the complex plane is this length right here is 2 square root 2, and this length right here is also 2 square root 2, it's just negative. And so we want to find the radius of this circle that it makes by finding the hypotenuse of this triangle. So this means r is equal to the square root of 2 square root 2 squared plus 2 square root 2 squared. And so, or we could just use the fact that it's a 45, 45, 90-degree triangle and say that, oh, the hypotenuse is going to be 2 square root 2 times square root 2, which is 4. And if you did this, you get the same thing. You get 8 plus 8 is 16, and the square root of that is 4. So in any case, r equals 4. And now for theta. Well, theta is just going to be the tangent of the hypotenuse, the inverse tangent of the, the opposite over the adjacent, right? So theta is going to be the inverse tangent of square root 2 over 2. Square root 2 times square root 2 over 2 times square root 2. Wow. Which is just 1. It's the inverse tangent of 1. Oops. All right. And the inverse tangent of 1 is 45 degrees, or we could just look at this again and know that it's a 45, 45, 90-degree triangle. So we have that r cis theta is 4 cis 45 degrees, or we can write it as cosine 45 plus I sine 45. But I'm just going to write this as 4 cis 45 degrees, or we can write it as pi over 2. Pi over 4, sorry. All right. Now this can be represented, let me erase this. This can be represented as 4e to the pi over 4i. All right, this is where it gets interesting, because if I told you, I want you to multiply negative pi over 2 or even better, if I told you to multiply, negative 1 over 2 plus square root 3 over 2i times 2 square root 2 minus 2 square root 2i, you could do it, right? You would probably do it, but, you know, if I have to do this, I'd groan a little bit. I'd just be like, ugh, okay, fine. Do I really have to? But when they're in exponential form, it is so much easier. Because if we look at numbers like this, and we know, hey, this is the same thing as multiplying e 2 pi I over 3 times times 4e of pi over 4i. Well, we know that when we have two numbers with the same base but different exponents, this is the same thing as the 4 as a constant. We can just put it ahead as adding the exponent. So this is e 2 pi I over 3 plus pi over 4i. And so yes, we're going to need to find a common denominator. But that is nothing as bad compared to what this is, right? I feel like there's so much more a chance of making a mistake this way compared to using this in exponential form. So when we make our common denominator, this just becomes, our common denominator is 12, so this will be 8 pi I over 12, and this will be 3 pi I over 12. So it'll be 11 pi over 12i. So this is 4e 11 pi over 12i. Anyways, I think it's much better to do it this way than multiplying that out. But if you want to multiply it out, by all means, be my guest. Another thing that's really nice to do with this is finding roots. Because let's say we wanted to find the roots of a complex number. Like let's say we wanted to find the roots of just 1. We wanted to find the 6th roots of 1. And like I'm sure, you know, 1 is negative 1 and the other is 1, but, you know, what about the other 4? So what we can do is we can say that we have to find the 6 roots of e to the, so 1 is equal to e to the 2 pi I, right? Because that's just, cis of 2 pi is 1. Cosine of 2 pi is 1 and sine of 2 pi is 0. So, but if we wanted to find the 6 roots of this, and these are all roots of unity, just so you know, because we can raise them to an integer power and get 1. Well, this would just be e to the 2 pi over I, so e to the 2 pi over I divided by 6. But also, because this is also equal to e to the 4 pi I, it's also equal to e to the 4 pi I divided by 6. And since this is also equal to e to the 6 pi I, it's also equal to e to the 6 pi I over 6. And so it's also equal to e to the 8 pi I over 6. And, you know, the pattern will keep continuing. We'll just add 2 pi over 6 I every time. So we start out with pi over 3 times I, which is here, and then we have 2 pi over 3, which is here, and then we have here, which, oops, I do not want to turn on sticky keys, which, let me do this in a different color actually, which, as we will know, is equal to negative 1, right, because cosine of pi is negative 1 and sine is 0, so yeah, that's negative 1. And then our next one will be 8 pi over 6, which is 4 pi over 3. And then the next one will be here because we're just adding pi over 3 every time. Oh my goodness, why does it keep adding sticky keys? And so our roots will be evenly spaced, and let me just draw our shaky lines. And they will look something like this, and those will be the 6th root of our number. So we could use de Moivre's, or we could just use this sort of method. In any case, exponential form is tremendously useful, especially when, you know, when you're multiplying complex numbers.